Bonjour, everyone. Well, we're back with another taping of Pathfinder in Paris. This is Ryan Duffy, your host, and rather than record an asynchronous intro, I'm going to do it right here with my guests. Before we dive in, huge shout out to the Euroconsult team for loaning us this lovely room at World Satellite Business Week, because free space is hard to come by, and quiet free space is even rarer. So joining me today is Brian Barritt, the Chief Technology Officer at Aalyria.
Right.
Aalyria. Okay, Aalyria. I got it. And you just announced yourself to the world this week. Is that right?
Did. Yeah, it's been an exciting week.
So was it time to coincide with this event?
Yeah, I think we knew approximately sometime around this we'd like to kind of emerge out of stealth mode and announce the new venture.
Okay.
And so it was kind of coming up around this season anyway, and we thought, it'd be a good thing to just time it and try to get it out. We missed it a little bit. I'll note, it would have been maybe better if we had gotten the announcement out like Monday morning, Paris time. It ended up being Monday morning U.S. time. So I think Monday at the conference, a lot of people missed the news.
The time differences are tough. So for a little bit more exposition, Aalyria is, I would say, kind of promising the world and then some, because there's of course a space angle here, and if you go to the landing page, which we'll link to in the show notes, it's connectivity everywhere is like the first sort of tagline you see. That is, I think, and we'll get into this, I think that's been a popular talking point and favorite line recently, just with all the announcements we've seen over the past few weeks and months. But then to give it a little bit more detail, Aalyria says that it is orchestrating networks at planetary scale, creating, organizing, and managing the world's most advanced networks to enable connectivity everywhere at the speed of discovery. And everywhere, that spans from air, land, sea.
Right. I think a lot of that is a nod to, there were two technologies previously developed at Google that are now part of Aalyria. The network orchestration capability, one of the things that's really unique about it is it supports terrestrial, air-to-ground, air-to-air. It supports ground-to-ground, maritime meshes. But as you get up into airborne and space, it's not only LEO and MEO and GEO, but the physics engine and the supports out to cislunar and deep space too.
Okay.
So, there's even a lot of the applications looking at stuff with NASA Near Space Network and the return to the moon, and things at Artemis that we're talking about supporting as well. So it really is a pretty broad set of domains and environments that we can support. Yeah.
So I think actually it would be good to establish the vocabulary. So these were the code. What were the code names?
Yeah, there were two code names inside of Google or Alphabet family. There was Minkowski, which is the software platform for kind of end-to-end path-aware kind of network orchestration. And the other one was called Sonora, which was the atmospheric free space optics project.
Yes, and now those two are Tightbeam and Spacetime.
Yeah, so Minkowski, we're calling Spacetime.
Okay.
Minkowski's a scientist. There's a tradition in Google of naming software backends after scientists in the area that we were. And it was kind of a network orchestration, kind of new kind of software-defined network that operates the network by keeping track of where things are in space and how they're moving across space and time. Minkowski was Einstein's professor, the inventor of space-time. So that's kind of the nod to the product name there.
Gotcha.
Yeah. And then the laser communications one was Sonora. We're calling Tightbeam. That's a little bit of a nod to the Expanse universe or other sci-fi that refer to kind of highly directional kind of laser links as tight beams.
Yeah. We're going to get into laser links and kind of dive deep into the technology, but rewinding a little bit, tell us a bit about yourself and you've been deep in this world. I was actually looking at your Google citations before this and looking, and you could see all the puzzle pieces start to come together. And I'll link to it, but what were you at Google, Alphabet? Yeah, Alphabet, obviously, for those unaware, is the parent company of Google.
Yeah. Actually, the origins of this tech kind of even predate that. I've kind of always been a space nerd, like I think a lot of us are that got into the industry and a computer engineering background. But a shout out here to NASA, who funded a research program at our university when I was in grad school, and we were looking at how NASA would kind of move, and this is kind of early 2000s and mid 2000s, but how NASA was going to move from like just circuits and bits to actual packets that hop across multiple things in space. One of the things that I think that work realized is some of the needs to like figure out how networks behave, not just links, but networks behave, and to be able to model them and simulate them really well. And I think that work led to other work, which led to advancements in being able to predict and model networks of flying, moving things really well. And that, I think, led to a realization that if you can model them and predict what they're about to do well enough, you can use that as a basis to operate them in real time and near real time. And led to the work later that we pursued in Google. But I was at Google, then Google X, and then Loon, an Alphabet company, for about 6.5 years.
Yeah, and my understanding is that Aalyria leverages a lot of the technology that was developed at Loon.
That's right.
For it.
Yeah, and this is actually, I'll actually say it's a little different than that.
Okay.
I think this is one that a lot of the coverage maybe framed maybe in a way that I think it could be framed better.
Okay.
At least for the software work, for neither of these projects, neither of them were originally developed for Loon.
Okay.
Google and Alphabet worked on a variety of ways to connect the unconnected for a number of years. Everything from low Earth orbit satellites to different types of high altitude platforms, solar long endurance gliders, balloon-based platforms, terrestrial mesh technology. And this is work that was intended to go across all of those projects.
Okay.
And that's why it kind of has the power and generality that it has, is because it was designed from the beginning to support ground and air and space and a variety of frequencies and spectrum types.
And so under the hood, a lot of this technology, I have here in my notes, antenna link scheduling, network traffic routing, spectrum. This one I wrote provisioning, but I think it was something different on the website. But authorization, or I'm not exactly sure. But it sounds a bit to me like this is kind of like an operating system in a way. Is that right?
Yeah, that's the right way to think of it. I think if you just think of any kind of like mega constellation you might imagine in your brain, right? And it doesn't matter if maybe it's satellites or it's high altitude platforms or it's something else. And let's say it's providing internet access to people. Well, when packets come in from the internet headed for that user, you have a bunch of decisions to make along the way. One decision is like, what is the physical link structure of the network? There's all these possible links between air to air, air to ground, space to space, space to ground that you might use. Maybe there's some could be optical, some could be RF. So which ones do you use when? But even before you've made that choice, like what makes a good set of links in one of these networks? Well, it depends on the end-to-end path and where you're trying to get data to and from. So this system will do everything from do the routing between the antennas and the attachment point deep in a network. It'll route traffic through there. It'll schedule all the handoffs between ground stations and aircraft, or aircraft and satellites and ground, and then handle the routing or of packets across intersatellite links and choices of frequencies and channels and bandwidths, all the way end to end through the network. Because all these things are really interrelated to each other. Yeah. If you solve one in a silo, you're kind of doing something suboptimal. And so it's really solving all of them at the same time in the most optimal way possible.
When you bring this technology into demonstrations and then eventually to market, what does the product look like? Is it a software subscription? Is there hardware involved?
Yeah, so Aalyria has two different products, right? But for the software orchestration platform we call Spacetime, that's available now. It was used in production on Loon at scale. Okay. There's kind of thinking about where it's physically deployed, and then we can also talk about kind of the end user's experience with it. In terms of where it's physically deployed, it runs on a cluster of computers. So it can be hosted in a data center. It could be as a software as a service. Maybe the customer has their own cloud environment they prefer it's deployed into. Right. So it can be deployed platform as a service.
So that would be probably like more government customers.
I think there's even a lot of commercial customers that maybe care about having control and maybe customer supplied encryption keys for their own kind of private cloud project they prefer it deployed into. Sometimes some want a turnkey software as a service. Some want it on-prem in like a hybrid cloud model. So we can support all of those things. Now, the way the end user experiences it, well, the end user just getting internet access doesn't kind of really know it's there. It just means the internet works and they don't experience packet loss or maybe TCP connection slowdown during all the handoffs and reconfiguration, because all of that happens smoothly without packet loss. But to the satellite operator or the HAPS operator or to NASA Operations Center that's doing end-to-end comms, we have a web interface for kind of situational awareness about what the network's doing. That I'm looking forward to getting all the product shots up on the site because it's real. We've got it now, but some of the cool features it has is you load it, you see like the globe, right? Everything that's flying around, maybe Earth, maybe lunar, whatever the setting is. And it starts out with a live view of this network. But you have this time slider, and you can just grab time and scrub time left and right. See all the satellites or the aircraft and everything reconfigure, and see the paths that everything was taking at what time. But if you click on something, it also gives you a bit of a view into what's happening in the ground routing, like behind your antennas on the ground, across the, kind of your ground-based network and how the data is flowing through that. So it gives you this full situational view and lets you kind of dive into things. Overlays weather, because sometimes we have to land the links from air or space to ground to dodge storms, depending on the link types you're using. It lets you overlay that information and lets you see all those things.
Right. A perennial problem with using lasers with these sorts of applications has been weather, right? What sorts of workarounds, if any, do you have to that? And I guess focusing on returning to the topic of the laser links and laser communications. What's new about the technology that you've developed?
Yeah, so we talked about Tightbeam and Spacetime, these kind of two products. So Tightbeam is laser communications, but it's coherent light communications designed to run through the atmosphere. So I'm not an optics or photonics expert. I've had to ramp up on it lately. But for those that are new to it, I'll kind of give the explanation that I came to understand.
That's much appreciated for all of us.
Most people that are doing laser communications are doing it with incoherent light or non-coherent light, where really it's the same as the light coming out of like a light bulb or something. It's doesn't maintain its order. And the way you send information is like the same way you would as like a Boy Scout with a flashlight. You like are flashing it on and off. And if you flash it on and off fast enough, you can send information that way. It's called on-off keying. You're just keying the light on and off to send information. Coherent optics is where you maintain the order of the light and the photons as it's transmitted, and that lets you do the kind of modulations that are used in radio frequency communications and get much faster data rates. And that's where with Tightbeam, our data rates through the atmosphere start at 100 gigabits a second per wavelength of light and go up from there, because you can get a lot more information through. Or if you don't care about the data rate of information, you can get more signal strength in exchange, more dB, decibels of link margin in exchange. And that can be really, really powerful. We're not the first people to try to do coherent light free space optics. I think what we believe is the differentiator with what we're doing is that, one, it was designed from the beginning to solve the problems of lasers through the atmosphere. So space to ground, air to ground applications was from the start with a team that has a long heritage of working on those problems and flying those things with a lot of flight hours. And we're doing some novel things to really correct for what happens to the light as it goes through the atmosphere.
Yeah. And I mean, on the you've demoed this, right? Right. I recall reading in the article that you've demonstrated this technology. Can you say a little bit more to the extent, it's not privileged, confidential, like?
No, that's right. I mean, we have we have an aircraft with these terminals mounted to them. We run a link to the aircraft. It can provide demos to customers that want to see it, that it's real and it works. Running at these data rates for an air-to-ground link. We also maintain terrestrial links for demos, long-distance ground-to-ground links all the time from our facility in Livermore, California. For people to kind of witness. And the conditions that the link can survive.
Yeah. So I'm going to ask an explain it to me like I'm 5 question here. But ground-to-ground, can you say a little more about how that works? And this is, we're a space publication, but that, given the topic and given like the area that
right,
what you're building.
So when you're trying to prove out this kind of laser communications technology, like the hard part's getting through the atmosphere. And when you're trying to do it with coherent light, you need to correct for all the disturbances so it all is still in order. Mm-hmm. So for a ground-to-ground link, you need to pick two locations that you could see it, right? You could look through a telescope and still see the other point. Yeah, you have to have line of sight.
Yeah.
But if you're running it, say in the San Francisco Bay Area, there's sometimes light fog, or there's heat, coming off the urban environment. There's atmospheric turbulence, like the same reason that like stars twinkle at night. It's because the light from it to your eye as it goes through the atmosphere is getting disturbed. So you kind of have to undo that effect.
Yeah.
And so getting really good at running a long distance link from, say, the top of a building to the top of a mountain in an environment like that, where you have that kind of heat and fog in the Bay Area, and working through those problems. When you then transition to space applications, you're often going through less atmosphere because when you go a very long distance link, there might be more net atmosphere between those 2 points than when you raise that link straight up into the sky.
Yeah.
You only go through so much atmosphere, then you hit the vacuum of space where things are easy, relatively easy.
Yeah. And if I remember my drone license test, it's a very interdisciplinary test, but the air gets thinner.
Yeah, right.
Yeah. I have to renew it soon too. So it's kind of, in a way, this is like studying up. And you envision that, I mean, kind of the like, I think one of the animating principles, if I'm understanding correctly, and correct me if I'm wrong, but is interoperability here, and the ability, to talk to various types of systems. Is that right?
Yeah, that's right. I think sometimes the relation between the two products and what we're really going for of a company can be a bit confusing to people. To use your analogy of like an operating system, like we invite and are happy with everyone to write kind of like device drivers, right, to hook up their switches or onboard processors or their ground terminals or antennas or their free space optical terminals to work with this system. We're making all of the APIs open. We're actually working to try to contribute them in open industry consortia to make them like open standards, so that everyone can plug in and integrate with everyone else, like from a vendor standpoint. Between network operators that adopt Spacetime, we think we can offer unprecedented, way more flexible ways to coordinate with each other. If two networks are both using this, whether it's on spectrum or internetworking or sharing ground stations. So we think that's really powerful too. I think the way to think about our hardware product with Tightbeam is it's something that you can get as kind of like an optional add-on that comes pre-integrated with this operating system.
Okay.
But you don't have to take that.
Yeah. The issues of spectrum authorization and all of that, it's wild. It's super complex and nuanced, and it's like the beefiest part of the aerospace industry, I think. But with Tightbeam, what sort of regulatory authorizations and like licenses would you need, and how would that be different than the traditional way that we communicate with satellites and satellites communicate back to ground?
Yeah, I think that's one of the things that excites people about optical, about laser for air to ground and space to ground, is that my understanding is there aren't spectrum licenses required to do that. The wavelength that people usually use for the laser, 1550 nanometer, my understanding is it's eye safe. That wavelength, the light bounces off your retina, it doesn't even go into your eye. So it's eye safe technology. It's technology that really doesn't really cause interference. It's really just it's like a laser link from one to the other, and you don't really have the kind of spectrum coordination required. I think historically people have wondered, well, what about weather conditions it can't get through? Those are always there. And I think that's where the power of these two products combined comes in, because we really need to move from thinking as an industry about the uptime of an individual link to the uptime of an end-to-end network path to a customer. And if you're looking at laser space to ground for like backhauling data in a network, the Spacetime platform can analyze at scale every possible link between everything and everything else in your network, including the effect that weather's having on every possible link across everything. and then it's going to choose links and evolve the end-to-end path structure of the network, including dependent inter-satellite link routing and other things, to land that traffic where that weather won't impact you.
Yeah.
And that really lets you, I think that's a required breakthrough to operate laser space-to-ground and air-to-ground links at scale as a production network.
It probably goes without saying, but behind the scenes, this system is running some pretty advanced models, I'd imagine, deep learning models and everything. And in that regards, did the sort of the association, and actually I do want to ask about this. I want to ask about this next, but the association with Alphabet and obviously Google's one of the leading research institutions, but also practitioners of AI, broadly speaking. Did that sort of pedigree help in developing this?
Yeah, absolutely. Like I don't want to speak too much on behalf of Google, so I'll talk about just my personal experience. But I had not had personal experience building kind of software services with high availability, uptime, and scale, like at these scales, prior to working there. And it's great to be surrounded by people who do that every day for other services that people know and love that run at really large scale, hosted there.
Yeah.
And so to be surrounded by those tools and that infrastructure and those other people to help you understand how to build and architect a system like this to run at that scale, it was definitely impactful.
You're hitting the ground running in a way, right? Because Aalyria was as being dubbed in the articles that have been written so far, and it's the first 3 days or so, or 4 days, I guess now. The Paris time difference is messing me. Yeah. But you spun out of Alphabet. Is that how you would describe it?
Yeah, I think spin out means different things to different people.
Yeah.
So I think the right way to describe it is Aalyria, the entity, acquired this technology from Alphabet.
In exchange for I'm an equity stake, probably.
So I think all I can say there is Google, Alphabet remains like a minority owner and shareholder in the company. But it's important to stress we're an independent company.
Right.
This is not an Alphabet company.
You read my mind because I did want to ask. I have that in my notes here. You're independent, like full stop. There are, of course, there are like other bets. Like before we were recording, I was talking about how in a past life, I covered Waymo pretty closely and Wing pretty closely. For those who don't know, those are the self-driving and drone delivery ventures. At least Waymo has shifted a little bit in that it's taken some outside investment, but independent entity, full stop. Say a little bit more about the backgrounds of the team and headcount, what that looks like. How, you're as I understand it, this is pretty groundbreaking technology and like really pushing the boundaries, cutting edge stuff. But it's a relatively small team.
Yeah, I think we have probably close to 30-ish full-time people right now, maybe into the 40s if you count some of our part-time contributors. And the vast majority of the team are the people that worked on the tech before, like inside Google and Alphabet. I think that's something that also says a lot. The folks working on Tightbeam worked on it right up and until we're now Aalyria.
Yeah.
But the people working on this tech on the Spacetime side and Project Minkowski, had a bit of a period of uncertainty, when the tech kind of got put on the shelf a bit, when kind of the last of the Google and Alphabet aerospace network projects kind of wound down with Loon.
Yeah.
And I think a lot of the fact that so many people believed in this so much to try to come back and support it and help it from whatever they were doing also says a lot about how much everyone believes in the technology and is proud of what we built.
Is it just kind of a product of right time, right place, or is, it's people say, timing is everything, but as it relates to Tightbeam, and then I guess we could also apply the question to Spacetime, but specifically with Tightbeam, I think that the amount of work that you see happening in the space industry, like Starlink is obviously putting the optical intersatellite links into their production satellites, and there's just a ton of other activity which we cover very frequently in the Payload newsletter as with laser links. Has their time arrived? And if so, what's the fundamental reason? Like, are there breakthroughs in hardware, that sort of thing?
I think I'm not sure. I'll speculate a bit in terms of why we're seeing so much of it now, and how we also think about Tightbeam and ourselves and our strategy as it relates to that, is that as the capacity of these networks grow, and if you look at the cumulative annual growth rate of data consumption in the world, right? Like, people's appetite for data is like insatiable.
Yes.
People keep thinking of their next generation constellations, lower altitudes, more capacity, more spectrum, more data. And even if you're using inter-satellite links at tens of gigabits a second or higher, usually people think of the space-to-ground link, at least for a constellation with inter-satellite links, as maybe aggregating the capacity across multiple serving satellites.
Yeah.
So if you're aggregating that capacity and you're talking about inter-satellite links of tens of gigabits a second, and you must think you need those for a reason, usually you're thinking about a space-to-ground link in excess of those data rates.
Yeah.
Right? And there's just a limit to how much data you're going to push with RF. And if you try to approach those data rates with radio frequency, you're often moving into the V band or E band or frequency bands where you anyway have these sort of weather phenomena are problematic, right, with droplet sizes or rain or different things. So solving these things at a network level and bringing these sort of capacity, we think the people that need space-time are often the people that will also need Tightbeam. It's like your constellations are getting more complex. You're adding inter-satellite link routing. Maybe you're doing a next-gen constellation at a different altitude with your first-gen constellation. Or you've got a MEO fleet or a GEO fleet you want to interoperate. So you're getting multi-altitude, you're getting multi-orbit, you're getting all the, maybe your mix of radio and other technologies at different bands. And so you can't just build something special purpose anymore for a certain orbit and a certain frequency and leverage some repetition in the geometry of your network.
Yeah.
You need this full-blown flexibility. And because of that same complexity and scale, you probably also need more data to the ground.
Yeah.
And Tightbeam will be important.
Yeah. So at a really abstract level, if you're talking about a satellite, like historically, that satellite has been designed to point in one direction.
Right.
And you see the rise of the multi-orbit and that sort of thing. And I forget who, but I was speaking with Capella Space, which is based in San Francisco. Building a SAR constellation, but they go up to I forget whose constellation, but that's kind of, that gets to the essence of what you're saying, right? It's not your grandfather's satellite constellation in a way, because like they're pointing in multiple directions. Yeah,
that's right. I think maybe I'll take it to two places, both of which I think need something like space-time now because of how they're changing. If you were doing an Earth observation satellite before, some polar orbiting thing with a sensor, you'd acquire imagery or whatever your sensing is, and when you eventually got over a ground station, maybe around the poles, you'd downlink it. Well, a lot of those companies want to get more real time, lower latency. They maybe have inter-satellite links, or they want to be really intelligent about how they downlink, and they can point an antenna one way while imaging a different way. So you have a need there. And then for communications constellations, same thing. I mean, geostationary satellite or something that had some body fixed beam. That's just a constant cone. And it's bent pipe and a ground station's always in view. That's like a whole different thing to what we're seeing people propose now with these regenerative mega constellations with inter-satellite links and multi-orbit things.
To utilize this, is it only satellites going up from here on out? Like, do they don't need special sort of...
No, we're really designed to overlay with where you are today and then support your growth. If you wanted to update, say, your ground station software or your spacecraft payload software to talk natively and directly to space-time, that's fine. But that's not practical for everybody. A lot of people are like, hey, I can't change that. It's on orbit.
Or especially like the ones up in GEO.
Yeah, right. Like where I've got...
Been up there for a while.
Yeah, or I've got... Or maybe just the person you'd have to ask to change it. It's just impractical for you.
Yeah.
So maybe you have some existing thing on the ground, some piece of software or hardware or appliance or whatever it is, that talks some proprietary format to tell that comms payload what to do or to control those ground stations. So our kind of software APIs for Spacetime, we have kind of two sets of software APIs. There's one that faces kind of the infrastructure, we call that the southbound. And there's an API that faces kind of like your business intelligence, we call it like the northbound API. But the southbound API is really set up for adapters. So you can take like a whole class of, say, satellites or certain ground stations from a certain vendor, and use our APIs to kind of auto-generate the code that you use to just make a pluggable adapter to convert our format to your existing heritage one.
Mm-hmm.
So that can get you kind of help you gracefully transition what you got now, and then we'll kind of support that future growth.
When you're talking about communicating with an asset that just in the most simplest terms is farther and further away, and you have hit on this a bit, of course the technical terms that you use completely escape me now, but let even just a low Earth orbit versus geostationary orbit, like how much there's got to be some sort of, and the word in my head right now is like packet loss, but like the strength of the link must weaken, right?
Yeah, I think there's two challenges that you can think about with distance and how our stuff relates. For Tightbeam, for a laser link, even though we think of a laser as like a pure point to point, there's still some diffraction, of the laser link.
Yeah,
it still fans out a tiny bit as it goes out in distance. So yeah, that translates to effects either less photons getting through or more data rate challenges or something. So
right.
There are challenges associated with distance. On the network orchestration side with Spacetime, when you're trying to tell communications assets what to do when, the longer distance you have, the more you kind of have to forecast the motion that's coming with the orbit propagation, even multi-body, because we support deep space and cislunar, and understand what's about to happen before it's going to happen, and then give that link or that radio or that gimbal enough information about where the thing is it needs to link up with, say, minutes from now, to do that. Another effect that you get into with the deep space stuff, because we're in a lot of conversations with NASA, not only for lunar but for some of the deep space, kind of Mars and other deep space networking, is there's a technology called DTN, or bundle protocol, for storing and forwarding data in transit.
Yeah.
So to orchestrate that stuff, you have to keep track of how much like memory can each node store.
Yeah.
And kind of plan when they're going to have links with each other, but kind of model the rate at which the data at the source needs to get to the destination, and what intermediate nodes are capable of store and forward versus which ones aren't, how much they can store, and kind of help with kind of this schedule-aware graph routing in a delay-tolerant networking sense.
That's fascinating.
And supporting that as well.
Super fascinating, super mind-blowing. And as you get further and further out to deep space today, you have to deal with what you have. And compared to a mission that you could send to some theoretical point in deep space today with today's technology, like that memory and the communication, like it's not going to be the same as what already is out there. So would you theoretically one day be working like with or alongside a deep space network, that sort of thing?
Yeah, we'd love to. I mean, I think we're in I would call it preliminary conversations with them now, but I think the community that works on like the interplanetary networking group is looking a lot about what's the best way to do routing with store and forward for deep space, and yeah, I mean, in those kind of networks, you're anyway planning the sets of point-to-point links between things in advance, and then using that information to plan how it should be routed along with consideration of storage is something that our system can easily support, because it already is modeling all the forward motion and is helping with that link planning.
Yeah. Man, this is some deeply technical, like multidisciplinary stuff. And to that end, actually, what parts of the technical roadmap, and you're the perfect person to ask this to, what parts of the technical roadmap, Aalyria, are de-risked? What sort of engineering problems are quote unquote solved? Because a lot of this sounds like kind of boundary pushing physics stuff. I suppose like the corollary to that is what would you still need to kind of prove out? Yeah,
so we'll kind of talk about those on both products. I think on the Tightbeam side, I think we feel like as a team, we're at the forefront with coherent light at these really high data rates and correcting for the atmospheric disturbances. We think we have some novel things there. We're doing a lot of things other people have looked at, and then we think we're doing those and more. And I think for an airborne terminal, we've got a lot of flight hours, and we feel pretty good about air to ground. But we don't have a space grade terminal that's flown in space and been space qualified.
Yeah.
So I think that's a lot of what people are looking forward to there, opportunities to put this thing on orbit, partner with somebody, and really get that done. I think on the Spacetime side, we have a production grade service available now. It's been used on Loon with over 2 million flight hours of comms payloads, multiple continents, hundreds of thousands of unique users. So it's been production deployed. We can deploy it now. We've finished porting it kind of off of Google internal infrastructure onto a public cloud environment, and we can do demos, turn up instances that could be used in production now. Some of the things we look forward to doing with it, I'll say one is our scale can support up to 15 million possible links in a network. That sounds really huge. It'll support pretty much any mega constellations scale today. But one of the things we're interested in getting into is helping people coordinate networks with other networks. As we kind of grow the network effect of adoption of people using Spacetime, we think there's a lot of power in really interesting ways to coordinate networks with each other, helping operators coordinate them with other people in ways that are way more flexible and way more efficient, or even share assets. I think we see today, ideas of ground station as a service, and people doing scheduling just satellite to ground station based on intervisibility. I think what we're looking at is doing that on a network path-aware basis across, air to space to space, like all the way along the whole path.
Yeah.
That kind of model, and the ability to have some neutral infrastructure that can be shared across things. Building out support for that kind of federation across multiple instances of Spacetime.
Right.
Is not only one of our big roadmap items, it's something we're really interested in. But that also necessitates even more than 15 million possible links in the network when you start pushing those things together. And that's also really well aligned with what you see as the visions with NASA's transition to the Near Space Network or other government initiatives to build hybrid space architectures. Is kind of looking in that direction.
What are some future sort of use cases that you see, terrestrial maybe, that you see? I think the canonical one might be plain Wi-Fi, because a lot of people are familiar with the trials and tribulations of using plain Wi-Fi.
Yeah.
And some of your marketing materials on the website or something, I saw, there's drone. I mean, there's of course so many different ways that this could be used. Is it premature to be thinking about that or no?
I don't think it's premature to be thinking about it. I mean, this stuff's. I think it's good for me to caveat that we're getting into the realm now of kind of the fun stuff we think about maybe doing with the tech. It's still a ways off, and I don't think anyone's sharpened the pencil too deeply on this stuff. But we are definitely getting good enough, or believe we are good enough at kind of understanding at scale how the position, let's say, of an aircraft, and even the bank angle it's about to happen, even if it's human piloted, would obstruct a laser link or something.
Oh, wow.
Even for an air-to-air or air-to-ground. So if you imagined the density of commercial air traffic, right, in let's say even over the continental United States or something, could you build a Tightbeam mesh between all that commercial air traffic at hundreds of gigabit a second without using satellite, and our aircraft stacked up close to each other when around takeoff and landing, that you could hop from the airport up to the air at shorter distances and build some sort of mesh like this? Is that practical? Would the commercial model ever work? Not sure, but those are interesting things to explore with this kind of technology. If you could bring hundreds of gigabits a second to an aircraft, that's a gigabit a seat kind of numbers, and those things are really interesting.
And I suppose actually that's another corollary to the question that I asked earlier, and it really just gets to the cost curves of all of this and the commercial viability. I would imagine that deploying this in production is not cheap, and so I guess the second part of that is would you what's your roadmap in terms of work? I'm imagining you probably work with civil space, militaries, that sort of thing, or enterprises that are less maybe price sensitive, and this is just enabling this for some sort of mission critical application is important. Is that a good guess? Can you speak to are you already in customer? I mean, obviously you mentioned that you're working with some. You have talks and you've demoed this and that sort of thing, but I guess what kind of segments and I'll limit it to aerospace
Yeah.
do you anticipate working with first?
So in terms of customers of this technology and who's likely to be first, we kind of are thinking about it on a need basis. So if you have a constellation up today and it's working fine, and let's say it's a specific geometry, it's a specific frequency, maybe what you have now is fine, or you can build something very special purpose and special tuned and simpler for that exact geometry and frequency and altitude of a satellite network. So on the other side of the coin, though, there's people who today need multi-orbit or even multi-domain, as they call it, like air and space and ground meshes all together. They need the full complexity of what we've built, and but it to be still elegantly deployed and high available and easy to use. So I think that's where the strongest pull comes from first. And so whether that's some of the people you might think of that are trying to do constellations that mix, say, a maritime mesh and a space component, or something where they're putting up a second-gen constellation at a different altitude. There's pull there on the commercial side. And then on the government side, whether it's civil government or defense, there's people who already have those same needs. And I think those are like the first movers for us. And
then I guess bringing this back to Earth, geographically speaking, there are obviously I think an easy way that I envision this is just all of the parts of the world that are out of cellular connectivity, and I think that was also what Loon was getting at. Like bringing connectivity to these places where it would never be economical or cost effective to lay fiber or build telco networks. Like, is that where again geographically speaking, like you see this being deployed first?
There's a definite geographic component, but I think of it a little differently. Like if you imagine like holding a flashlight above a table, right, and shining it down. You kind of illuminate a small area if the flashlight's right over the table, and then as you raise it up, you cover more. There's more light shining, more area, but it's like less. It's like more diffuse. It's like fainter per every like square inch of the table, right? And I actually think of connecting the unconnected in a very similar sense. You've got like something that emits energy. It's like a radio, right? And if you're at the height of a tower, all of that bandwidth is over a small area, so you get a lot of data rate per square kilometer. And then as you raise altitude, you're often getting more coverage area, but you get less megabits per second per square kilometer. Well, population density on Earth varies 5 orders of magnitude. Like there's places on Earth that have like 2 people per square kilometer, like Saskatchewan. And then there's like downtown Manila, which is tens of thousands of people per square kilometer. So you have these like 5 orders of magnitude. But a lot of what that kind of indicates to you is there's no one-size-fits-all solution for connecting the unconnected from an altitude standpoint. You'll never do it all with towers, and you'll never do it all with satellites. And interestingly, single kilometers of altitude is like, okay, you can think of as like tower. Tens of kilometers, think of as like HAPS. Hundreds of kilometers, that's LEO. Thousands of kilometers is MEO, and tens of thousands is GEO. And so we really think the solution for connecting the unconnected is a mix of terrestrial base stations, high altitude platforms, LEO, MEO, and GEO, all working together. And there's parts of the world geographically, like you mentioned, where there's an optimal altitude almost for that population density, and it's clumpy and it's non-uniform. But the solution to connecting the rest of the world is like all of the above.
And all the above. That's literally what I was going to say. But I think that's a good note to close out on is connecting the unconnected, because that's what all this is about. But I'd be remiss to not do my classic end of show, really rapid fire. Do you have any role models or anyone that's particularly inspired you over the course of your career?
It's less of an individual. I think like technology areas inspire me. Like at different times in my career, I've headed down paths for different reasons. A place I want to work, or a work-life balance I want, or something. But it's really great to like be energized and excited. I think I've just enjoyed chasing things to work on that I want to nerd out on. And enjoying it. I've had a lot of great mentors along the way and support. I think a lot of the people early on, even in the NASA world, I think kind of helped inspire me to get into this area.
Do you like sci-fi?
Love sci-fi.
Yeah. What's your favorite? I mean, it's a broad question. It's a super broad question.
I'll give a plug right now to Project Hail Mary with Andy Weir for anyone that hasn't read it yet.
Okay.
His sequel, The Martian, just finished it. Awesome.
Okay.
It's a fantastic novel. It's probably my favorite right now on the recent side. I think people listening will probably know Tightbeam's a little bit of a nod, maybe to the Expanse universe. Some people have noted there was a prior Star Trek reference. I think Tightbeam's appeared a few times in sci-fi. But yeah, a little nod there as well.
We'll include all that in the show notes. Next one would be hottest space take or most contrarian view on the future. And I typically will say space economy, but it can be, can widen the aperture a bit. It could be space exploration, I don't know, that sort of thing.
Hot takes. All right, I'll give a hot take. I don't think HAPs are dead.
Okay.
That's my hot take. I think there are some very interesting
high altitude platforms.
Yeah, sorry. High altitude platforms.
we got 55 minutes through.
Yeah,
I forgot the
thanks.
But
yeah, atmospheric satellites.
Yeah.
I used to get more traction calling them atmospheric satellites. I think it makes people. It's the right framing for those systems. I think towards the tail end of Loon, we got very interested in kind of aerodynamically shaped, lighter than air vehicles.
Yeah.
That could have. If you mixed what we learned on Loon about using AI to change altitudes automatically and find the best winds with just enough kind of lateral propulsion, right, propellers to go, laterally around, to overcome those, to use as a combination, rather than building a monster airship that can punch through any wind.
Yeah.
That combination of the two, I think, is really compelling. And I think there are people out there that don't get a lot of visibility who are working that problem, and I think they could be very interesting. And I think they're very compelling platforms to use in hybrid networks with satellites, places where space-based systems will sell out of capacity. We already see that with some of these mega constellations. It's places where people don't have terrestrial internet. They can't get good DSL or cable or fiber. But Starlink or whatever it's going to be, Kuiper or something, sold out.
Yeah.
And the ability to take a 20-kilometer satellite, because that trade-off I talked about with altitude and density, slot that thing in and operate it as a hybrid network, plug and powered by Spacetime, right? Because we support it. I think it's not dead. I think there's still something there.
Yeah. Last question, I suppose, is where if all goes to plan, where do you see yourself in Aalyria in 5 years?
I would like to see Spacetime become kind of the de facto, kind of open, neutral platform for facilitating orchestration of aerospace networks and coordination between them.
Awesome. Actually, and one more. Do you have any concerns about any of about aliens piggybacking on or intercepting or anything, any of your communications or networks or anything?
Hey, the nice thing about laser links is you got to be in the beam.
Okay.
Right?
Okay.
So,
okay.
Thanks for the last opportunity to plug low probability intercept and jam. Yeah, it's one of the perks of lasers.
Oh, hopefully none of the aliens are listening to this. Yeah. Brian, thanks so much for coming on.
Hey, thanks a lot. Appreciate it.
Okay, folks, if you like what you heard, leave us a rating and review on your podcast player of choice. It will really help, and it's much appreciated. As always, you can reach out to me at ryan@payloadspace.com with feedback, tips, or just to say hi. Pathfinder is brought to you by Payload, a modern space media brand, and it's easy to remember. We publish Payload, we publish Pathfinder, and we publish Parallax. So check out those other properties if you haven't already. That'll do it for now, though. I'm Ryan Duffy signing off, and I'll see you back here next Tuesday.